section 6.3, vectors in the plane. So we're going to look at this idea of a vector that represents the motion of an object, which is really hard to do. How do you represent motion of an object? Simply and consistently. So vectors is our best way to do that. And we're going to look very surface level at some characteristics of vectors. So vectors encompass a force and a velocity. So we have a certain amount of motion in a certain direction, going at a certain speed. So to represent all of that, we use vectors. Visually, they are rays with an initial point and a terminal point. And then this notation from initial to terminal, from P to Q, and then this little kind of like harpoon looking hook for notation over P and Q. So the ray or the directed line segment, so again vectors have a direction. It has an initial point, and in this case, that is point P, has a terminal point also. In this case, it's Q. And then the length, or what we call magnitude. Because again, like, how do you draw how much force is behind something? Or how do you draw how much velocity something has? So how we represent it is with length. So the longer a vector, that is symbolic of a greater force or a greater velocity. So because it's length, we can find that by using the distance formula or the Pythagorean theorem. Vectors are usually denoted by bold lowercase letters. So I'll try to draw a bold letter, but U, V, and W. Those are usually the three letters we use to denote vectors, U, V, W, and we use the bold rather than using the 2 points, the initial and the terminal point. Now, component form of a vector, that's kind of how we generalize vectors. So we assume that the vector is starting at the origin and the component form then uses the initial point or the origin as the initial point. And it's a way to take initial terminal points and kind of boil it down to horizontal and vertical movement. So how much horizontal force does a vector represent? How much vertical force does a vector represent? And then you put horizontal and vertical together, you could get a diagonal. So standard position is then how we create component form. So we take any vector we have and we adjust it so that the origin is acting as the initial point. So let me scroll down a little here. Here we are. Give myself a little more room. So finding component form and magnitude of a vector that has initial point 4, -7, terminal point -1, 5. So let's say this is P and Q. So then P sub 1, P sub 2, and Q sub 1, and 5 is Q sub 2. So to find component form, to put this into standard position, so component form of our vector, say it's P and Q, do that hook over the edge. Now the notation we use, it's like, looks like an ordered pair, but just these sharp corners. So not parentheses, but like that. To find the component form, you want to find the horizontal and the vertical. So Q1 minus P1 and Q2 minus P2. And then you close with that sharp parentheses. So doing this arithmetic, -1 minus 4, -5, and 5 minus -7 to get 12. So we have component form of that vector. And if we want to, we could say this vector is a vector V. And we could say -5 is V1, 12 is V2. So if we wanted to, we don't have to, but we have the option to. So to find magnitude also, remember, magnitude is the representing the length of the vector in the plane. So when we're finding length, we want to use distance formula or Pythagorean theorem. And if you already have component form, you can just use Pythagorean theorem. Kind of simpler, but you get the same results. So magnitude, we do a double absolute value bars. It's almost like we ran out of symbols, so we just started adding them up. Like on vending machines, instead of A, B, C, and then you have two major choices, so you do A, B, B, C, C. So finding magnitude, doing the Pythagorean theorem with our component form. So V sub 1 squared plus V sub 2 squared. So our -5 squaring that, and our 12 squaring that. And you get square root 169 and 13. So component form, magnitude, using your initial point, your terminal point, to get it in standard form or component form, and then you can use that, or you can use your initial data to find magnitude. So that's kind of the first thing, or first or second thing. There's a lot in this section to look at. So vector operations. So if you have a vector representing a force and a velocity and a distance, you can of course have different objects colliding with each other or interacting with each other. You could have an object get a boost or a hindrance applied onto it. So vector addition, have vector u, try to make that bold, plus vector v. And when you do that addition, It's really as simple as adding up the horizontals and the verticals. So u sub 1 and v sub 1, adding those up, and then u sub 2 and v sub 2, adding those up as well. Scalar multiplication, so when the vector gets multiplied by some scalar to increase the force or decrease the force. So some scalar multiple times u. That scalar multiple just gets applied to the horizontal and the vertical. So k gets distributed to the horizontal u1 and the vertical u sub 2. So take a moment to pause the video, look at examples A, B, and C, then check your work with my completed notes. And then also looking at direction angles. So a vector, if I skipped ahead, let's go back. Okay, so a vector has a force or velocity and it has a direction. So where is it going? It has so much force, so much velocity, and that force and velocity is going that way. And we want to be able to say what that way is. And we do that by using direction angles and some of our trigonometry from the unit circle. So remembering quadrant 1, 2, 3, and 4. Quadrant 1 is 0 all the way up to 90. And right now we use degrees. But of course, if you wanted to, you could use radians. So 0 to pi over 2 radians. Quadrant 2 encompasses direction angles from 90 to 180. Quadrant 3, 180 to 270. And quadrant 4, all the way around from 270 up to 360 degrees. So when you use your trig functions, sine, cosine, or usually we're going to use tangent. You can use any you want, but usually we use tangent. It's important to remember, based upon your components, what quadrant are you in? And then your answer should fall into one of these ranges, or you should make it fall into one of these ranges. So example A, looking at vector u, we're going to find the magnitude. Now magnitude is Pythagorean theorem if you have component form. Luckily we have component form. So the magnitude of u is going to be the square root of 3 squared plus 3 squared. So that's going to give us root 18. Which if we break that down into simplest radical form, this is root 9 and root 2. So root 9 gives us 3 root 2. To find our direction angle, so direction angle or theta, here is the easiest formula you can use. use the inverse tangent of your vertical over your horizontal. Remember, sine is y, cosine is x, tangent is y over x. So tangent y over x, your vertical over your horizontal. So 3 over 3. And you plug it into your calculator, or you kind of see, hey, they're the same. So you end up with 45 degrees. Now that's good, because 3 comma 3 is in the first quadrant. So our angle 45 should be between 0 and 90. That works. For example, B, 3 comma negative 4, to the right and down, so we're in the fourth quadrant. So our answer should be between 270 and 360. But, like the problem with the law of sines, the ambiguous case, your calculator will give you the first answer for inverse tangent. So the answer you get, you'll have to make it fit into this range. You're going to have to adjust it. So take a look at the rest of the examples. Check my completed notes online.